Hello guys, so welcome back to my new YouTube video. So today we'll be going to discuss about a nuclear fission. So what is nuclear fission? We'll be specifically discussing about this only, like what is a kind of reaction that takes place at that time in a nuclear fission, and how is nuclear fission different from that of nuclear fusion, and what is a nuclear reaction, how does it takes place, how does it leads to that much destruction. We'll be going to cover everything in this video today, so let's continue it ahead. So do you know about him, like who is he? You must be able to see J. Robert, but the surname must not be visible to you. Oppenheimer. So he's J. Robert Oppenheimer. He's none other than the father of atomic bomb discovery during the World War II, the time when atomic bomb destructed everything in Hiroshima and Nagasaki in Japan. And at that time, he was handed over with the project, Manhattan Project, and he is the director of that project, and he discovered the atomic bomb at that time. So he is a great personality. Okay, so why there is a need for atomic bomb? Like it's needed in a World War time. Other than that, it's also a renewable source of energy. We'll be discussing about it ahead. First of all, let's discuss about atomic bomb. Like, uh, think about it. What kind of energy this takes place? Like, what kind of reaction this takes place inside an atomic bomb? And what kind of energy is converting in the atomic bomb? Tell me about it. Uh, Take a moment, pause, and think about it. Yes, it's a nuclear reaction that takes place inside an atomic bomb. But how is this nuclear reaction different from that of a chemical reaction? Have you ever thought about it? Let's figure it out. हम पहले chemical reaction के बारे में जानते हैं. Like what is a chemical reaction? And how is that different from a nuclear reaction? So, in a chemical reaction, there is an involvement of a nuclear, sorry, uh, there is an involvement of an electron, outer shell electron in a chemical reaction. There is a transfer of electron or a sharing of electron between the two elements or two or more elements. Here we are having an example of sodium chloride, that is an ionic species, means they are having the ions like positive charge and a negative charge. As you can see, the electron is transferred from the sodium outer shell to the chlorine outer shell. Chlorine in outer shell having 7 electrons, and when one electron transferred from sodium outer shell to chlorine, then chlorine octet completes and that gains a negative charge. The one which is accepting the electron, that is gaining a negative charge, and the one that is giving a electron, that is gaining a positive charge. So here electron is coming into usage. But in a nuclear reaction, as the name suggests, the nucleus is taking part here. So, nucleus of an atom is involved, and nucleus consists of proton and neutron. Okay, so change in the nucleus takes place in this reaction. So, if nucleus is changing here, this must lead to a conclusion that the element itself changes. Like on a reactant side, in a chemical reaction we have same elements on both the side, like on a reactant side and on a product side. But in a nuclear reaction, the element itself changes because the nucleus is coming into existence. The nucleus is involved in a reaction that leads to change in a completely new nucleus. That's why the nucleus is changing from the earlier, or we can say from the previous nucleus. So let's see how is it taking place. See here, we are taking two isotopes of hydrogen, deuterium and tritium. So they'll be having a different mass and the atomic number is same. So when they are colliding, what is happening? The helium is produced. Like, how is it taking place? Because the nucleus of atom is involved, that leads to a fusion, lot of energy is released, plus the that leads to a formation of helium plus some neutrons. Okay, so this the what is this, helium is produced, as you can see here. So we'll be discussing about nuclear fission in detail. So nuclear reaction is of two types, as you can see here, nuclear fission and nuclear fusion. I'll be giving you some of the points like how they differ from each other, but specifically will be more focused towards nuclear fission. Okay, nuclear fission, fission itself says split up. Like, how's it splitting up? We'll be seeing here. See here, the small neutron that is very unstable is colliding with a heavy nucleus, like a small neutron that is coming, it's colliding with the heavy nucleus, it split that heavy nucleus into two small nuclei. Okay, so as you can see here, this big nucleus split up into two small nuclei. Here see, two big small nuclei, this is a here a big nucleus splitting into small nuclei, plus some some neutrons are also there. That neutrons are also splitting up and a lot of energy is produced. So this is a nuclear fission reaction. Now let's see what is nuclear fusion reaction. It's specifically related to bombarding. So what is taking place here? As you can see, the deuterium and tritium, when both are combining together, leads to a formation of overall new element, that is nuclear helium. Helium is formed here along with the formation of energy, plus some neutrons are formed. Okay, see here, the neutron is going and the helium is formed here. After helium I have written plus neutrons. It's difficult to write over here. Okay, so this is a basic difference. Like in a fission, there is a bombardment of a small neutron with a big nucleus, but in a fusion, they fuse together different isotopes of hydrogen or isotopes of any other species, or they are fusing together to form a completely new element, that is helium. Along with that, the energy is produced plus some neutrons to balance out the reaction. Okay, so let's discuss nuclear fission in detail. So this is a nuclear fission that takes place. Firstly, the small neutron is coming from this side, that is colliding with this larger nucleus to split up into two lighter nuclei. As you can see, this one nuclei here and another nuclei here, they are it's forming two small nuclei, plus the spark, that is the energy, tons of energy is released. Along with that, some neutrons are also released to balance out this reaction. Here, see this reaction, three neutrons are released here, है ना? 1, 2 and 1 is here also. So the reaction we can like say low energy neutrons when combining or bombarding with heavy nucleus. We can't take any nucleus that is heavy, we have to take only radioactive nucleuses. So we are taking uranium, plutonium and thorium in this reaction. These, when they bombard together, this leads to a formation of two lighter nuclei plus tons of energy is reduced and n number of neutrons are released. Okay, n number of neutrons, tons of energy and two lighter nuclei. So let's discuss in with one more example. Let's see, here we have taken uranium 235 and combining with the neutron, okay, leads to a formation of barium and krypton. Okay, so barium, see here, barium is formed and here krypton. See, barium and krypton, they are moving in an upward and downward reaction. When then that barium, krypton plus some neutrons are formed. Two neutrons are releasing here, as you can see. Two, one is here and one is here. See, two neutrons, and these are for the uranium 235. So uranium 235, when this neutron, the neutron that is released by here, they'll be further combining with uranium 235 that is there, and that leads to a chain reaction taking place here. Two neutrons are released. Okay, so we have seen that the nuclear fission and nuclear fusion, both the reactions are chain reactions, and that will goes on and on by itself, and that leads to a large scale destruction, and that will be over years and years on that upcoming generations and generations. Okay, so here we are taking one example of a nuclear fission reaction. So that is a small neutron, here you can see, is combining with a large uranium 235, that leads to the formation of barium and krypton. They are moving like upward and downward, and that leads to a formation of three neutrons. Three neutrons are formed in this reaction, and these three neutrons are further combining with uranium 235, and that leads to a formation of further three neutrons, and they'll further combine with uranium 235. So the reaction will goes on and on. Let's see here, like this, here uranium 235, here is also uranium 235, and one uranium is here. So let's see it again. This uranium 235, then these three neutrons combining with uranium 235, three sparks will be produced, as you can see here. That leads to a formation of further three neutrons. They'll be combining with further uranium 235, and the reaction goes on by itself. Okay. So this is in an uncontrollable manner, and that takes place inside the atomic bomb. When we use atomic bomb, then this is a kind of uncontrollable reaction that takes place, and it is not controlled by any human or external factor by outside. The reaction goes on and on by itself, and that leads to a large scale destruction. But if we use this nuclear energy in a controllable manner. So this is an atomic bomb and a nuclear power plant. The in both the sides we are using a nuclear reaction, but in an atomic bomb we use the nuclear reaction in an uncontrollable manner, and that leads to a large scale destruction. But in a nuclear power plant, the reaction is in a controllable way. That's why we are using this energy, the nuclear energy, to convert it into a to convert it into a electrical energy. Okay, so like why we are shifting towards it, uh, the because in a nuclear reaction there is nothing like a CO2. Like CO2 is not formed in a nuclear reaction. So CO2 is as we know that CO2 is a main component. Carbon dioxide gas is a main component of greenhouse effect, and it is a main component that traps the heat energy and doesn't allow the heat energy to go outside the earth layer. Like it traps the heat energy inside the earth atmosphere. It doesn't allow the energy to move out from the earth atmosphere, and that leads to a heating of the earth nowadays. And that's why it is a sustainable way to it is a nuclear energy. Nuclear power plants is a sustainable way to produce electrical energy that will be without the CO2 consumption, CO2 formation. Like in a combustion reaction, there is a formation of CO2 gas. The vehicles that are the diesel or petrol vehicles that release CO2 gas, and that leads to a production of CO2, and that is a main constituent of greenhouse effect, and that's why the nuclear power plants are necessary. But the main disadvantage of these nuclear power plants is their cost of investment is really very high. But after that, the um, benefits are really very good. So this is a nuclear fission reaction. Here, what is happening, like we have bombarded the nuclear 235 with the neutron that leads to a formation of barium and krypton, plus 3 neutrons are formed plus a energy is formed. Here, the as we don't here calculate the elements element wise. We don't do it like that in the nuclear reactions because the nucleus is changed, so we can't do that because here we have new uranium, and on a right hand side we have barium and krypton. So how can we do that? Okay, so we'll be doing here by the mass concept, and that mass with the E is equal to mc square, the Einstein equation formula. We'll be putting that mass here, and we'll be finding the amount of energy that is formed here. Okay, so E is equal to mc square. C is the speed of light, and m is a mass. That is the mass. Will be subtracting this mass from this side and mass from that side. So the atomic numbers and mass numbers are balanced here. As you can see, 92 plus neutron mass is 0. So sorry, it's a atomic number. So the atomic number is same on both the sides, left hand side, right hand side. This is for the atomic number, and this is for the atomic mass. Okay, so mass here is 236, here also 236, but we have found that a mass on a reactant side means mass on this side is higher on that the mass on this side. Okay, so the mass on the left hand side is higher than on the mass on a right hand side. Okay, so we'll be subtracting those masses, and we are getting here as 0.2 AMU. So 0.2, like after putting all the values, these minute values also, like up till 2 decimal point we are putting mass here, so we'll be getting zero point 0.2 AMU, zero point 0.2 AMU mass. So means 0 0.2 AMU masses form. Masses, this is a loss in mass. Okay, so this loss in mass is giving us energy. This mass is converted into energy. So by the formula E is equal to mc square. Wait, let me change. E is equal to mc square. So for 1 AMU we can have the mass of electron is 1.66 into 10 raised to power minus 27 kg, and the speed of light is 3 into 10 raised to power 8 meter per second. After putting all the values, can you see the amount of energy that is produced? 1 point, I'm sorry, 4.98 into 10 raised to power 37 joules of energy is released. 10 raised to power 37. Like, this much energy is produced by zero point 0.2 AMU mass. So can you imagine if we will be taking different elements on both the side and will be bombarding them, then if that mass is higher, then how much energy that will lead into conversation? Yeah, it will be very huge and a large scale destruction will be takes place. So here we'll be ending our topic. That's it about the nuclear fission reaction, and do subscribe my channel for more such videos. And if you find this video helpful for you guys, then please do like, share, comment, and do share this video with all the students who will be like you only, who wants to learn these concepts but maybe facing some kind of difficulty in understanding from anywhere. So if you find it helpful, you can share it with your friends. And yeah, thank you so much.